you going to put this video on the Facebook group?
I don't know. I need to get this off the fix it. This is not my iPad.
Alright.
It's the first time I'm here outside of the marketplace.
All right, shall we begin? Okay, so hi everyone to the CS Maths sesh. First of all, thank you to Sarah for organizing this. And everyone can hear me all right, yeah? Okay, so just a bit of a preamble. So we had a chat with Sarah last week, or was it last week? I don't know. And we said that some people are slightly confused by math because they haven't really encountered it at uni level. And basically I said I would be happy to give this sort of tutorial. So if you like what I give you now, then please give us feedback and maybe I can do it more than once. I have material for at least 3 of these occasions. So if you think this style or some other style would be useful with this theme, then please let either me or Sarah or both of us know. And second of all, about the format. So we have 2 hours. This book is room for 2 hours. Is that right? So we have it until 4. So I don't know if you had a look at it in the Facebook group, but basically I posted a long list of things that I have material for. Basically I have material for the first 5 of those chapters that I put online. I hope to cover the first 4. It would be dreamy to cover the first 5. Probably will cover the first 3. It really depends on how you're feeling about it. So the way I was planning to do this is try to do half-an-hour installments, and then after half hour you can ask me questions if you're confused. If this doesn't work, let me know and then we'll change it. Okay? So you might want to turn around because I'll be writing on the whiteboard. So maybe if you just took your chairs and like sat there because you won't see anything, and it would be nice if you like if we move these chairs like behind this table maybe. Is that okay? I mean, you can sit in the corner there if you really don't want to be in the front.
I'm fine. I don't need a desk.
Sure. It's just find yourselves. Jalaj, can you? If I'm writing on the board here, can you write what I'm writing here? Is that okay? Okay. I just want everyone to see if they bother to turn up, you know. Okay. So, cool. Let's begin with the material. So, the first chapter is on, or first section is on sets and logic. So, basically, I want to sort of make this material as self-contained as possible. I want to have as few bits left unknown as I can, so that you can refer back to stuff that I said here instead of trying to find it elsewhere online. So we will be. So that's why we will start with the most basic thing that we will build from, which are sets and logic. So I like to begin with what a set is. Okay, so a set. Okay, either there or in the corner, maybe there. So set is basically, for our purposes, is only going to be a collection of things, right? It can be anything. And this sort of notion is, it focuses on the idea that for us a set is just going to be a collection of things that are of interest. And here I'm leaving a lot of things vague because it's a very broad notion. So a set could be anything from some numbers, which are very abstract, or it could be just the set of all the desks that are in this room. It could be the set of people registered as a student at the university, anything along those lines. So just to begin with things, a bit of notation. So I will try to have as little notation as possible where I'm allowed. Notation is useful for communicating things, right? That's what basically math is all about. So I am forced to use at least some. So, and by the way, the first 3 or 4 chapters are high school maths. So basically it's just a reminder in perhaps a more uni-level setting. But the math itself is not going to be hard at all. Okay, so a set. We denote sets with usually the capital letters of the Latin alphabet. So A, in this case, I could say A is a set. And then I could define what a set is. This symbol is, you would read it as defined as. Defined as. And then for a set, we denote this with curly brackets. And here we can list the elements of the set. And here it can be anything, right? So it could be a number. It could be a string. It could be the name of someone. It could be anything, right? If I want to refer to an element of the set, an element of the set is going to be a lowercase letter of the Latin alphabet, usually. So in this case, I would say A. And now, so A could be 1, A could be the string AB, or Tom Kelsey. Now, if I want to express the relationship between A and small a and capital A, then the way to do this is through this symbol. This is read as in or element of. So you would read this as A is an element of A, capital A, okay? So just to give you another example, if I have B as my other set, and that would be 2 and 3 and say the string C, then the following are true statements, okay? And we will come to what a true statement means. Okay, so 1 is an element of A. If we want to express that something is not an element of something, then we just cross the element, this operator over. So 1 is not an element of B. Okay? Fairly simple. Now, an important property of a set is its size. We will mostly be operating with finite sets. There are infinite sets as well, such as the integers. To denote the size of a set, we put 2 bars next to the name of the set. Okay? So this would be, we would read this as the size, or sometimes the cardinality. This is a mathsy term, so I won't use it. But it's sometimes called the cardinality of A. And this, for finite sets, literally just means count how many elements are in here. So in programming terms, this is the length of some collection. So in our case, the size of A would be 1, 2, 3. Okay? Just a quick poll. I want to illustrate some of my points with programming examples. Is there anyone who is not familiar with either Haskell or Python? Or JavaScript? So everyone knows what lambda functions are. Is that right? Is there anyone who doesn't? Or is it like, no, okay with that? Or maps and filters and reduces? Cool. That makes my job very easy. I mean, yes, in some sense. Okay. So, this is basic. These are some basic notions and notations for sets, and now we're going to look at operations between sets, and I'm not going to delete these just yet. Okay, so these are the most important parts. These are the most important operations for a set. So the first thing that we can have is a union. Oops. Oh my god. And it's denoted with sort of a U. That it's not really the letter U, but it looks like letter U for union. It's written as this, and this is going to be the set which contains all the elements of A and all the elements of B, but all the elements in it are unique. Okay, so I will now use a different A and a B to illustrate this point slightly better. So instead of C, I will have a 4. And instead of Tom Kelsey, he has to go 3, 4, 6, let's say. So A union B, I will just look through these elements and combine them so that I only have unique elements. So I have 1, 3, 4, 6, 2, 3, 4, but see, 4 is not unique, so this 4 goes. 3 is not unique, so this 3 goes. And now I have a unique set of elements, so this is the union, okay? Similarly, I can have an intersection. An intersection is all the elements that are common in A and B. So in our scenario, 1 is not in B, so it's not going to be in my intersection. 3 is in B as well, so that's in my intersection. 4, that's in B as well. 6, that's not in B, there's nothing else, right? Okay, I also have difference. So difference is a funny thing. So we write A difference B or A minus B. This set is going to be all the elements of A that are not in B. Okay? Now this can sometimes be confusing because there can be more elements in B than in A, but that is not important in our case. What is important in our case is we're just looking at if something is in B, then we're not going to put it into, is in A, but is in B also, we're not going to put it in our set. So here, 1 is not in B, so that stays here. 3 is in B, so it is thrown out. 4 is in B, so it's also thrown out, and 6 is not in B, so that stays as well. Okay? This is not a symmetrical operator, because B difference A is now going to be all the elements of B that are not in A. So now I have to go through this set instead of this one. Okay? So here 2 is not in A, so that's get put in. But 3 is in A, so that gets thrown out. And 4 is in A, so that gets thrown out. And the fact that there's a 6 here, that doesn't matter. We don't care about that. Okay, so the only thing that stays here is 2. Cool. Okay, 3 more operations, and we're through with this. Subset. So this is not an operation, this is a relation. So we will say that, now forgetting the concrete examples A, B, we will say that A is a subset of B if all the elements of A are in B as well. So if if this was my B, my collection of things, right, then this would be a relation like this, right? So everything that's in A So this could be my case, okay? So everything that's in A is also in B. Now, a slightly confusing property of this is that a set is a subset of itself, because a set contains all the elements that it contains. I know that sounds a bit twisted, but it's true. Okay? There's a stricter version of this, which is called proper subset. So that is without this equality line here. And this disallows this property. Okay? So this says that A, all the elements of A are also in B, but B contains at least one element that is not in A. Okay? Cool. So just again a couple of examples. So if so take A and B, and now I'm going to create a C, and my C is going to be 3 and 4. Okay. I should have put the dots there as well. So I will define C as 3 and 4, and now if I just want to write a couple of example relations, A is not a subset of B, but C is a subset of A. In fact, C is a proper subset of A. C is also a subset of B. Okay? Cool. I don't know if I want to. I'm going to erase these. Okay. Apologies for the lot of erasing. Very confined space. Okay, so now I'm going to turn our attention to a bit more of a constraint scenario. So when we're talking about something within set theory and in terms of perhaps functions, we like to think about a set that contains everything that we care about for the current purposes. This set we will call the universal set, is usually denoted U, so this is called the universal set. This, again, is whatever the purpose, this is basically all the things that we care about. So for example, I could come up with any set, but when I'm talking about counting stuff, then I don't want to consider the set of strings. I don't care about that. So I only want to care about the set of integers. So the integers would be my universal set. Okay? The reason why we need the universal set is to define the final thing that I want, the penultimate thing that I want to mention is the complement of a set. So a complement of a set is either denoted A bar or sometimes also denoted as A with a C written on top of it for the word complement, and it is defined to be as everything in the universal set that is not in A. Okay, so for a complement, I need a universal set and a set of whose complement I'm looking at. Okay, so just to give you a couple of examples, if my universal set is, I'm going to define my universal set as the integers from 1 to 10, say, okay, then I have, let's have 7. Then I have A, the complement of A is going to be, with respect to this universal set, is going to be, well, 1 is in here, so that's not going to be in the complement. 2 is in here, 5 is in here, and 7 is in here. Okay? okay, actually 2 more notions to go. Sorry, I need to put this here. So one thing that I should have mentioned at the intersection part is that there's a special case when if I have a set A and a set B and I take their intersection, if their intersection is empty, there are no elements in here, then A and B are called disjoint. So in this scenario, we call these sets disjoint. And a special property of disjoint sets is, so usually if I have 2 sets A, B, they would look like this. If they are disjoint, then this middle bit does not exist. Okay, so there's nothing in here, so they are better drawn as separate blobs. Okay? And it's really easy to see then that the size of the union of 2 disjoint sets is going to be the size of A plus the size of B. Okay? This is if A and B disjoint. Okay? Cool. Otherwise, we could look at what would happen if we had an intersection. Okay? So in the general case, if we do have an intersection, then if I want to look at the size of my union, the size of my union is everything that these 2 blobs contain. So that is going to be the size of A plus the size of B. Okay? That's the size of this blob plus the size of this blob. But then we notice that this middle bit got counted twice. So we subtract the middle bit, and this middle bit is exactly their intersection. And this formula here, this is called the inclusion-exclusion principle. And this is an important thing. We'll come back to this later when we're talking about probability. Just quickly checking, can everyone see what I'm writing on the board?
Could
Yes.
you just move to the right
Sure,
next
sorry.
board after finishing?
Yeah, sorry, I will. Just make myself a bit more space.
Thank
I
you.
don't think your iPad's really picking up what's on the screen.
Huh?
I don't think your iPad's picking up what's on the screen.
Okay, well,
Sorry.
we'll have to look into better recording technology. Okay. Where was I? Cool. So the reason why I mentioned this here is, here you can immediately see that because the complement of A is defined to be everything in the universal set that's not in A, I'm going to erase some stuff. Their intersection is going to be disjoint. And this is a key point. So the intersection, oh, this is really bad. The intersection of A, and the complement of A is going to be disjoint. It's the empty set. Okay? So the size of their union is going to be the size of the universal set. Okay, and the final thing that I want to cover before moving on from sets to the next thing is called the Cartesian product. And the Cartesian product of 2 sets is basically forming tuples from the elements of two sets in question, and we want to include every combination. So let's see. So again, I have my set A and my set B, and I'm going to define their Cartesian product as all the tuples in A and B. So what I mean by that is I'm going to pair everything with 1 first. So I'm going to have the tuple 1, 2. I'm going to have the tuple 1, 3. I'm going to have the tuple 1, 4. And then similarly, I'm going to have the tuple, so now I'm going to pair 3. I'm going to have 3, 2, 3, 3, 3, 4, and then the same for 4, so I'm going to have 4, 2, 4, 3, 4, 4, and then lastly for 6 really quickly, so 6, 2, 6, 3, and then 6, 4. Okay. Okay. Before I move on to the next part, 30 minutes have just elapsed. So, are there any questions so far? It can be the simplest question. I'm here to help. No? Cool. Okay. In that case, we will move on to the functions. Okay, so what is a function? A function probably could be best explained in terms of a lookup table. Okay, so in maths, functions are basically lookup tables. We have a key for this lookup table, and then we have a value. So a function, I'm going to define a function as something that takes a key, and this key will have some type A. Well, for our purposes, types and sets are sort of interchangeable. So I have a type A, and I will give back something of type B. So for example, if I have my set A, and I will have a set B, let's have a different set B this time, I'm going to have the string AB and my string Q, for example. Then a perfectly good function, this is Haskell notation. Math notation would be saying that the set is being mapped. Okay? This is just, I probably shouldn't have written type variables, and I don't want to confuse you too much. But the point is I'm going from one set to the other, and I can write down my entire function. My function is just going to be a list of tuples. So I could say 1 maps to AB, 2 maps to Q, 3 maps to Q, and 4 maps to AB. Okay? And then when we say we apply the function or get the value of a function, we give the function something from our first set, and then we'll get something back from our second set. Now again, for just some notational purposes, this first set from which we're going, I should write it as this in general, so this is going to be my A. This first set is called the domain of f. And this second set is called the range. This is going to be my B. And in fact, I could have, let's have a scene here. So all a function is it takes everything from A, this is important, takes everything from A and maps it onto something in B. So this would be my function f. So in our case, A is 1, 2, 3, 4, B is C, A, B, and Q here. Okay, and to get the value of the function, I just give it some element of A, for example 1, and all f does, it looks it up in my lookup table and then gives back the second part of my tuple. So f1 is going to be AB. Now this definition of function, what mathematicians use, this is what mathematicians use. In programming, this is something more restricted than what we normally understand as function. In programming, this would be called a pure function. Okay, and I'm really sorry, but I need some more notation. Again, this subset to which I'm mapping, this is called the image of f. So this is called the image f. And if I know this, then whatever maps to this is called the pre-image. So here, this would be called the pre. Now, to avoid confusion, the domain and the range are different from the pre-image and the image. The domain is the whole thing that is mapping down here. And the range is the set we're mapping into. The image is defined for any subset of A. Okay? So the image of the entirety of A is this, but see 4 and 1 map to AB. So the image of this subset, the image of 1 and 4, would be just AB, okay? And whatever maps to AB, which is 1 and 4, is called the pre-image. Okay. There are a lot of terms, and I do apologize about it, but I will need most of this to establish a lot of stuff later. But basically, the idea here is think of functions as lookup tables. Okay? Now, the next thing that I'd like to talk about are distinguished sets that have some that we use so many times that we just have a symbol for them, and then we all understand what they are. So the two sets that I just really briefly like to mention, in fact 3 sets, are the natural numbers, which are denoted by this n. They are all the counting numbers, so they are literally just 0, 1, 2, 3, up to infinity. We have z. These are the integers, so they are all the natural numbers plus the negative numbers. So we have up from negative infinity, we have -2, -1, 0, 1, 2, blah, blah, up to positive infinity. And then finally, the last distinguished set that I'm going to mention here is going to be the set of Boolean values. There's no real standard notation here. I'm going to just call it B. This set is, it has 2 elements. It has the value true and the value false. Okay? So, these are all the distinguished sets that I'd like to mention. I will mention one more soon, but not for the moment. Okay. Now, everyone has covered Boolean operators, right? So we know what AND means, we know what OR means, we know what all these other things mean. I don't really want to go over them because I think everyone here knows what they are. I just like to point out that you might notice that there is a really close correspondence with between Boolean operators and set operations. Basically, if you stare at these things long enough, you'll realize that intersection corresponds to and union corresponds to OR. But I won't really go over that now. Okay, so I would like to mention now that we know these special sets, I would like to mention a very special kind of function. I'm going to call it P or Q. And these are the kind of functions that take something from any set and they map into, I probably should, okay, I will make this I will put a bar here where I'm talking about the Boolean set to distinguish between just any set B. So again, B just contains true and false, okay? These kinds of functions have many different names. In the thing you will find them as premises, they're also called propositions, they are called properties. In programming, they're usually called filters for a reason that will become clear quite soon. So an example of a filter would be, I'm going to define set A again. So I'm just going to say there's going to be the integers from 1 to 6. Okay? And now I'm going to define a filter. I'm going to call them properties from now on because it's more appropriate. So I'm going to say that my property is going to be that A is even. Okay? So now if I draw up the function diagram, then I have 1, 2, 3, 4, 5, 6. And so this is A, this is B. So here, I mean, I'm treating this quite formally, but it's quite intuitive what this does, right? So this will map to true from all the even numbers. So 2, 4, and 6 will map to true, and 1, 3, and 5 will map to false. Okay? The preimage of true in properties here, that the preimage of true, these numbers are called the truth set. Now, this is unimportant. What is important is it's also called a filtered set. Okay? So basically what I'm saying is that if I look at the preimage of this, 2, 4, 6, then I basically filter the set based on this property. Okay? And this is a very crucial thing that we always do in programming. We always want to filter stuff that we don't care about. Okay? So just to give you a really quick example in Python, to write my property P would be lambda x, and to test evenness, we do a mod by 2. So this property is exactly this in Python. Okay? So this immediately leads on to the next thing that I want to talk about, which is set building. So the moment we have some sets, we might want to build other sets out of them. Okay? And premises are a very important way to do this. Okay? So the way we're going to build sets, and this is called set builder notation, if I'm going to create a new set C, what I'm going to do is I'm going to say, we put a bar in the middle. If I want to build a set C from some other set A, I'm going to say, I'm going to borrow all the elements from A. Okay? So I'm saying I want to borrow all the elements from A. Now, I'm going to filter them. I only care about the A's that have some property that I'm interested in right now. And finally, to the filtered set, apply some function f. Okay, and this is how set building works. So, but this function could just return A itself, okay? So you don't need to put a complicated function here all the time. So to give you a Python example, in fact to give you a couple, so staying with this property here, if I have my A as, let's see, sorry, in Python it would be just zeros, right? It would be, say, 1 to 10, okay? Then I can create a new set C where I say, I used AB, let's call it B. For B in A if P A. In Haskell this could be written slightly nicer because it corresponds to this notation a bit better. In Haskell this would be written as something like a, I can't remember, it's not a bar, is it? Or is it a bar in Haskell? I'm not sure. I feel really stupid. I think it's a bar. I'm not sure. So it would be, sorry, let's not confuse ourselves. Be A such that P, sorry, that should be a B there as well. Okay? So you can see that this really corresponds to filtering. In fact, an even nicer way of writing this in Python would have been C equals filter P A. Okay? Yeah. Cool. Let's see what I have next up. What's the time? Okay. Right. Okay, I want to spend very little time on something called quantifiers. This is not super related to DE, but it's going to be incredibly useful later. So if we want to talk about elements of a set that have some certain properties, then there are two crucial things that we'd like, that we usually talk about. Is one thing is if there's a property that every single element in the set has. Okay, so if I have my property Q, Q of A as is an integer, okay, then every single element in A, in my example set A from 1 to 6, all of them are integers, right? Now if I want to communicate that to someone, then instead of writing every single element is an integer, I can just say for all, this symbol is read out as for all A in A Q. Okay? So what this says, this means that for all A in capital A, I have the property Q satisfied. Okay? And when I say a property is satisfied, it just means that if I substitute my my element into Q, I get a true value. That's all it means for it to be satisfied. Okay, so this means that every single element I plug into my Q, I will get true back. Okay. And the other quantifier is called there exists. So this is read out as there exists. So this is an upside down A. This is sort of a mirrored E. This is read out as there exists. Again, we need to say an element in A such that Q. What this says is there is at least one element in my A that satisfies Q. Okay? So for example, if my Q was this, then because every element has Q, it is trivial that there is at least one. Okay? On the other hand, if I had P, and P was that A is even, this is still a true statement, right? Because not all of them are. So now for all P, this is now not true, right? Which is false. Don't know why I said not true. So not all of these integers are even, right? So this statement is not true anymore. But there still exists an even number in A, okay? Cool. This also has some nice relations to set theory, but I'm not going to go there. Now, just as a final note, I'd like to talk about the negation of quantifiers. So, what I want to talk about is, if I have a statement like this, then what does it mean to say not for all A in A? Because some people, in fact not some, many people get confused about what this is. The opposite of this statement, right, is not at all for all A in A, not B. This is not true, okay? Because what I'm saying is not for all. So I'm saying that not every element satisfies this property. That is not equivalent to saying all of them don't satisfy this property. The correct thing is to say that there is at least one thing that does not satisfy this property. So the actual, so this is now true, okay? So the opposite of not all of them satisfy this property is equal to saying there is at least one thing that does not satisfy the property. Okay? And then similarly, not there exists a in A such that P is equal to for all A in A not P. So saying that there does not exist any element with this property is equivalent to saying all the elements satisfy the opposite of the property. Okay? Cool. That's all I want to say about quantifiers. I think I want to cover that. But do you want me to talk about mathematical reasoning, the proof techniques, the direct proof, proof by contradiction, and mathematical induction? Because I went through the DE lectures, and there are some proofs that use mathematical induction and proof by contradiction. I was just wondering if people were fine with that, or should we go on to probability instead? Who wants to go on to probability and skip proofs? Okay, that's like half. Who? So can you put your hands up again? It's very. Is that half at least?
You could just go over it quite quick.
The problem is that I don't. Huh? I'm sorry.
We do the probabilities first and then go back to it because I've got somewhere to be at half.
Okay, sure. Fine. Actually, we're just no, nothing against it. Also, we've just come to the second end of the half hour. So before I go into the next thing, I want to ask if anyone has any questions. Yes.
See, between that A and that P, is there a dot or is there a space?
Here.
Yeah.
Yeah. Sorry, there is a dot. The dot. Sorry, I should not have skipped this. My apologies. So the dot. I know that there's a lot of things that in maths looks superfluous. In math, a dot is read as such that. Okay? So to read this, it would be for all A in A such that P. Okay? The dot is basically to separate the quantifier from our statement. Yes?
See how you've got N for natural numbers, Z for integers, and B for Booleans. Is there one for real numbers as well?
Yes, that's right. So because we're not going to be using them, at least we might use them a bit, but then I would even have used the symbol. The set of real numbers is unsurprisingly an R. And thank you, actually, you reminded me. There's also a set of all the fractions. And the maths word for the set of all the fractions is the rationals. I don't know why they're called the rationals. Probably because 15th century mathematicians couldn't comprehend that there could be anything else than a fraction. And they are also denoted Q, which is really weird. But the set of rationals is a really good example of how we can use a distinguished set to build another really distinguished set, okay?
What's the line through it for? Is that part of it?
Yes, there's a line through it. So usually distinguished sets have a bar through it to distinguish them from just me writing a B or a Q or any other letter, okay? They're called blackboard bold for no reason at all, because they don't make it bolder, so whatever. There are a lot of things in math that are just named for no reason, or incredibly badly named, or there are 10 names for the same thing to confuse people. I try to not confuse, so I hope that I didn't manage to do well so far. Okay, so the set of rationals is the set of all fractions, right? So we can use stuff that we have already to build this, okay? So it's the set of all fractions. So what I'm going to say is I'm going to borrow two things. I'm going to borrow a P and a Q from Z, okay? So I'm saying borrow P and borrow Q from Z, okay? I'm going to put a restriction on Q. I'm going to say that Q can't be 0, okay? So this is my filter. This is my my premise or property, and then I'm going to say this is just P over Q. Okay, and this is the actual definition of the rationals, or a set of all fractions. I'm not going to use the word rationals anymore. Also, we're not going to use Q at all. So, but this is a good example of how set builder notation works. Yeah. So just to reiterate from set building, the only thing you should take away is the way set building works is you borrow some elements from some sets, you filter them, and then you apply some function to them, and that's it. That's all function building is. Okay, so let's go on to probability. Oh, before I move further, there's a really important thing that I need to cover before we go on, which are operations on special sets, numeric sets, in fact. This is not probability yet. This is still belonging to the set part. So imagine that we have some sort of set of numeric values, and by numeric, all I mean is if I have a set A of which A and B are members, then what I can say is I can add them together, and this will be some C which is also in A, okay? And I'm not going to say what addition is here, but you can imagine it as the addition on of integers or any numbers. And I can multiply them together, which is going to be some D, which is also in A. Okay? So just to give you examples, although I'm sure that this is the thing that I least need an example so if I say I have 1 and 3, which are in Z, okay? Then I can say that A plus B, which are in my case 1 plus 3 makes sense, and this would be 4, which is also an integer, so this is good. And similarly, 1 times 3 is 3, which is an integer, so this is fine. Okay, this is all I mean by this. Then, so this is the first part, and the second part is I can create an ordered collection that is comprised of elements from a set A. So, for example, I could have, so if my set is Z, then I could have 1, 1, 2, 3, 5, 8, 13, say, okay? In maths, we call this a sequence. In programming, we call this a list, okay? So I could have done this, so this is called a sequence in maths. Sequence, please. Or a list in programming, okay? In general, we would write the elements, we would write the sequence as AN, and we would write the elements as A1, A2, and I'm sorry for not starting with 0. We could start with 0. In fact, why not? Why don't start with 0? I know that you love it. I love it too, so whatever. Okay? And this goes up to AN minus 1. Okay? So this is a sequence of n elements, starting from 0 going up to n minus 1. So similarly, lists have a size of the list. This in Python, this would be len A if A was my list. So combining these two ideas, if I want to get the sum of all the elements of an. So basically I want to get the sum a0 plus a1 plus plus an minus 1. So mathematicians have invented for loops basically before for loops existed. A special kind of for loop which just goes through all the elements and adds them up. We call it sum and is denoted by capital sigma. We have an index in the exact same way we would have an index in a for loop. We start with 0, we go up to some value, and then we just say what we're going to add in every single iteration. Okay? And this is indeed a definition. Okay? Similarly, they've invented a special for loop for multiplying stuff, which is denoted by capital pi, read as the product, or productum, which is Latin for product. I don't think you could have guessed that. And is defined exactly to be a0 times a1 times a(n minus 1). Okay? And finally, they've also invented iterators, so we don't have to. So if I don't want to care about the index, I just want to add up the elements, then instead I can say take every single element, I'm going to use an E here instead, take every single element E in my set A or my sequence AN and sum up E. Okay? So this would be a for loop. This would be a for loop with an iterator instead of an index. Okay? In Python, this could be written as if I define the lambda function plus, let's call it plus because sum is already defined as something else. As lambda x y to be x plus y, then all of this could be written as, and I had some set an, okay, which is something. Then this sum is just reduce plus an. Okay, these two are exactly the same thing. Cool. So this is something that I wanted to cover before I go into probability. And now on to probability. So yes.
Can I just ask, so what did you call that top red bit? Like, what's the name of this thing when?
Say that again.
When an operation on elements of the set, or like the result is also part of the set, and a member of the set. What do you call it? Like, what's the name?
Adding them together. What?
No, I mean like, so there's an operation you do on elements of a set, and the result is also part of the set. What do you call it?
Or do you mean the property that if I add two things together and I get an element of the same set?
Yeah, what's the name of this
The name of that property is called closure, but I don't want to mention that because we're not going to use it yet. This is the closure property. So for example, okay, so just to give you an example, so if I had the set of the natural numbers, and then I subtracted 5 from 3, that would be -2, right? And -2 is not in the naturals, so that's not closed. It does not have the closure property. Is that what you're referring to?
Yeah.
But if I add numbers together, 1 plus 2, that's always going to be a natural, right? So two naturals added together. So we say that the naturals are closed under addition, but I'm not going to go into that because that's not necessary. Any other questions before I start on this? Okay. So I had some trouble coming up with a good way of explaining probability because I always ran into circular definitions. So I will apologize for some of the stuff that might come through as slightly confusing. What I will try to do is basically give you a motivation and then formalize something and then give you some other motivation, and then we will see how the whole machine fits together. It requires some bootstrapping if I don't want to explain everything. So what is probability? Probability is basically the art of, if we know something, then we're going to try to predict what will come next. And that's as good of a hand-wavy definition as I could have got. So I will immediately start with an example. So imagine a really silly scenario where there's a light and it's blinking, and it can blink in two different colors, okay? It can either have a green color or a red color, okay? And for some reason you're interested in finding out what the color of the next blink will be, okay? And you don't know what is controlling the blinking, so essentially to you it is random, okay? So how would you go about trying to predict what the color of the next blink is going to be? What you do is you just take your time, sit down, look at all the blinks, and just tally how many reds you see and how many greens you see. So all you would do is just sit down, and for every blink you record what blink you've seen, right? You tally all these blinks, and at some point you become bored, and then you stop tallying. And that's, you're going to say, is your sample set. And this basically, this is what based on which we're going to make our prediction, okay? So nothing formal here yet, we're just trying to get a sense of what we're doing. So then, if I ask you, what's the next color going to be? You laugh in my face because you say that question doesn't really make sense. What you say is, what does make sense is saying, what is the probability that the next blink is going to be the red, or what is the probability that the next blink is going to be green, okay? And the way you're going to tell me that is, you're going to say that the probability of, that's not an element, that's just an F. The probability of red, all I'm going to say is just going to be proportional to the proportion of reds in my recorded list. So all you do is just count up the reds. So that's going to be 1, 2, 3, 4, 5, 6. And you just look at the proportion of reds in the entire set of observations. So there's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 elements. I managed to make it completely symmetrical. This is not what I intended. So let's add on 3 reds, because we like to live dangerously. So this is now going to be 15 elements. So you're going to say that the probability of seeing red, yes?
Will it not be 9? Yeah.
Oh, sorry, that's right, yeah, thank you. Okay. So it's going to be 9 over 15. And similarly, you could say the probability of green is going to be 5 out of 15. Now then the question is, what do you really mean by saying the probability is going to be 9 out of 15?
6.
Oh, did I? Oh, okay, thank you. So then you could say, what does it really mean that, what do you mean by the probability of this is going to be 9 out of 15? Well, what you really mean is saying that based on my assumption that this is completely random, if you sat down for 15 trials, then I would expect that out of 15 trials you will also see 9 red and 6 green. Okay? So basically, what you've done without noticing, or maybe you've noticed if you're very clever, probably you have noticed it, is basically you've looked at all the things that can happen. What can happen? Well, we know that if we observe something, our observation can only be either red or green. Okay? And what we've done is for both red and green, you've assigned a number to them, a probability. Okay? Now, as it turns out, these are some of the key notions in probability theory. The set of all the things that can happen, we call it the event space, and is denoted by omega. So omega is defined as the event space. These are the events, all the events that can happen. Event space. Okay? And what you've done is you assigned some numbers to red and green. Okay? So we're going to call this assignment X. Okay? And we will say that this assignment of yours is going to be R and G, and it's 9 over 15 and 6 over 15. Okay? So basically saying, you're saying that with my definition, we're going to say that if I conducted 15 trials, I will see red with this probability and green with this probability. Now, the way you would do this, to formalize this into notation, you will say that the probability, which is again a blackboard P, so there's a P and there's a bar next to it. I don't know if in data encoding lectures do you just use a single P, or do you call it PR, or do you call it prob? Which one should I use? The blackboard P is the maths way of doing it. Should I just call P that? Okay, I will just call it P, but know that there's a bar missing. Okay, so the way we will say this is sort of a function. The only difference here, which is something I'm not going to go into, is what it really means to mean that this is random. We don't know. Okay, we're just going to accept that it is random, whatever that means. So we're going to say that if I want to know the probability of some event happening, right, I'm going to have some P which takes in something, one of my lookup tables, takes in my lookup table and gives me back a probability that is between 0 and 1. Okay? This by the way, is called the interval between 0 and 1. Not going to go into that. Basically, these are all the real numbers between 0 and 1, including 0 and 1. Okay? This is just for formalism. This is very intuitive. Okay, so for P, so what we're going to do is I'm going to give you a lookup table, X. Okay? And I'm going to say, can you look up green for me, please? And give me the probability of that. Okay? So this is saying, I'm going to give you my lookup table X. In my lookup table, tell me what is the probability associated to the element G. Okay? So this will spit out 6 over 15. Okay? So I should now give you the name of this X. This X is called a random variable. Random variable. Okay? And another thing, so we have the event space. A subset of the event space is called an event. Okay? I'm going to make that clear in a moment. So, then what we can do, yep, cool. Then what we can do is I'm going to use a different event space now because this is a bit restrictive. So now I'm going to think about dice rolls. So I'm going to say that my event space is going to be all the numbers from 1 to 6. Okay? And I'm going to say that this is going to be a fair die. A fair die just means that I would expect if I sat down for 6 die rolls, then I would see every single number being rolled once. Okay, that's all it means. So I'm going to define my random variable d as, well, at the top I have my possible values, and then below I have my probabilities. Okay. So, then again, I could say, well, then what is the probability that in my lookup table d is going to be 4? Well, that's just 1/6, right? But now what if we want to look at not just particular values, but as I said, this could be any subset, right? So here I can define any filter. Okay? So I can say, what is the probability? So this is basically a lookup function, but a bit more clever. That d is going to be even. Okay? So then, this will filter my d. Okay? My filtered set is going to be just t 1/6, 4 1/6, and 6 1/6. And then what p does, once it gets its filtered thing, it just sums up all the results. So my results will be a 6th, a 6th, a 6th, and I will just sum it up, which is going to be 3 6th, which is a 1. Okay? So in general, my p with some filter, I'm going to call it E for event, but you should think of it as queries basically, or filters. It will basically create a filter set f, and it will give me the probability of everything that's in my filter set. Okay? So this is just writing this in a more abstract way. Okay. So now I would like to go back to the random variable and this particular selector. What we want, so we want probability to behave as like vaguely nicely, let's say. This means that we want to exclude absurd things from our possibilities, our possible probabilities. So these values, we want to say they can't be anything. Okay? And the way we're going to do that is we're going to place some restrictions on what these random variables can be. So, and these are the two axioms of random variables. They're not really, but whatever. The first one is going to be that if I have some random variable x, so this is a random variable, then the probability of any one value with an X. So anything that's in X, anything that can happen, right? This is going to be bigger than 0. So all we're saying is probabilities can't be negative. Okay? It doesn't make sense to say the probability of this is minus 50%. That's just stupid. And then the second thing that we'd like to say is, again, if X is a random variable, then the probability of omega, so that is any of the events happening, this is going to be 1. So what we're saying is that if we're asking for the probability of any of the things of interest happening, well, one of them has to happen. So it should be 100%. Okay? What's the time? Is it half? Okay, so we're just approaching 3:30. Does anybody have questions? Or is it super basic and everyone gets it? Cool. So then, let's see. So you might ask, how do you come up with these numbers? So in the first example, I presented you with a method which is basically just observation, okay? And mathematically, an observation, we call it a trial, okay? So basically there are two ways, and this is sort of dabbling into philosophy, but just so for completeness, I'd like to mention this. So this is the original way, and some people call it the only proper way, okay? So what I mean by this is, here the way I assign these numbers is I actually went out in the real world and conducted some experiments. And then I came up with these numbers, and then I assigned them, okay? In maths, you can idealize things, and you can just say, I believe that with these assumptions, these will be the numbers. So what do I mean by this? What I mean by this is, let's say I have a coin, and I'm going to say it's a fair coin. And by fair coin, I mean, I would imagine that getting flipping a head or flipping a tail has equal probability. Okay? So the mass of the coin is completely, like, physically perfectly distributed. There's no flow in the coin or the way it's flipped. So then I would say that the probability of either head or tail is going to be half. Now see, here I did not conduct an experiment. I conducted the experiment in my head, okay? I just made some assumptions in my head, okay? So I can assign numbers like this. I can assign any number, in fact, to any of these set elements, as long as my two axioms are fulfilled, okay? Let's see. The first one, I will flip them. So these theoretical ones that we come up with, we've just assigned them. These are sometimes called the prior probability. They're called prior because they are before the experiment. And then we would go out into the real world, see if our assumptions made sense, and then this actual one, what the real world actually produces, that would be called a posterior one, because it's after the experiments are done. So posterior probability, prior probability. I don't think you use these words in the, but I think they come up somewhere else, so it might be useful. Who knows? Okay. So, what else do I want to talk about? Yes. So, mutual exclusion and independence. Okay. So, Okay, so are you sure there are no questions? Because then I will go on to the next bit of property. Okay, the event space can stay on, but we don't need. Okay. So I want to put D back in. Sorry. Okay, so let's consider two events. The first event we're going to consider, again, think of these as filters, is that the next thing that we're going to get from D is going to be even, okay? And then the other thing that I want to consider is that D is greater than or equal to 4. Okay, so these are different events of the event space. This subset is going to be 2, 4, and 6, and this one is going to be 4, 5, 6. Okay, it's really easy to see that the probability of this event is equal to this event. Both are half. Okay, so then one could ask the question: what is the probability that we have one event and also another event? Okay, so this would be the probability of the result of the dice for both being even and bigger than or equal to 4. Okay. Well, we can look at what these things filter to. Okay, so my first filter is just going to be, again, 2, 4, 6. My second filter is going to be 4, 5, 6. But the thing that both of them are true, I'm going to have to take the intersection of the two. So my actual filtered set is just going to be 4 and 6. Okay? And that's also the reason why sometimes people write it like this. Okay, so they actually put the union sign in there. Okay. So, okay, and then let's go to the other possibility, which says E1 or E2. So you guessed it already. This is going to be, sorry, I should have said intersection here. So here, similarly, these two are going to be the filters, but here, this or this, so that's going to be the union. So that's going to be 2, 4, 5, 6, right? And they get summed exactly the same way. So this is going to be, just for completeness, this is going to be 2 over 6, and this is going to be, so this is also written as E1 union E2, and this is going to be 4 over 6. So we could use the exact same rules that we knew from before. So we could use the inclusion-exclusion principle here, because basically that's exactly what we're doing here if we look closely. So in general, it is true. I will write this up here. So now going up here, the probability of some, this is in general, of some event and another event happening is going to be the probability of the event 1 happening. So this, looking at the property of this filter set, plus the probability of this filter set. But because now we double counted their intersection, we have to subtract that. Okay? So this is true in general. Okay. Now, there's a special case. If I define an E3 to say that, for example, D, so I'm defining this, right? So let's not confuse this. D is, let's say 2, really simple. Then notice that, say, event 2 and or event 3, their filtered sets are disjoint. Okay? So that will mean that this intersection is going to be 0. Right? Would you like me to draw it as well, or do you just believe me? Cool. So this will be P to P E3, and nothing to subtract because it's 0. In this scenario, when two events are disjoint, and this is the case, we call E2 and E3 mutually disjoint. Sorry, mutually exclusive. This means that if one happens, the other can't. Okay? Now, before I jump to the last bit of probability, does anybody have questions about this stuff? Yes?
What happens if we're trying to get the probability of event 3 and event 1?
I'm sorry?
What's the probability of event 3 and
Event 1.
Yeah. Since
So there you can see that the filter set of this is going to include 2, right?
Yeah.
So because E3 is going to be a subset of E1, we could just say, like, one route of reasoning could be, because this is a subset of this, it's just going to be the probability of this. Another way of arriving at the same result would be to say, okay, so what is the filter set of this? That's 2, 4, 6. So the probability of that is 3/6. Right? The filter set of this is just 2. So the result of that is a 6th. Right? So that's going to be, according to our formula, that's going to be 3/6 plus 1/6, that's 4/6. But their intersection, their only intersection is 2, probability of which is a 6th. So we subtract that. So 4/6 minus a 6th is 3/6, right?
Okay.
Does that make sense? Or are you, does it clear it up, or
Yeah.
is it good? Okay. Any other questions? Okay. So let's get to our favorite part of probability theory, conditional probability. So now, assume that there are two events, okay? So there are two different things that are happening or have happened that we're interested in. There's some event A that has happened, or some event, and some event B, okay? So this event will have some probability, and this event will have some probability, okay? So, if we are interested in the probability of both of these things happening, well, we already know we would just write the probability of A and B, okay? So if we're interested in what these two will be, at the same time, we just write this. But there's another awfully useful way of looking at this. Another useful way of looking at this is saying, let's assume that I know B. Well, what is the cost of me knowing B? Well, it is the probability of B, right? Because otherwise it's not B. Okay? So assume that I know B. Okay? What information does that give me about A? Okay? And this extra information, this extra nudge of information that knowing B gives me, the way this modifies this probability is called a conditional probability. Okay? So I'm going to say, so this is going to be the probability of A given B. Okay? So my original viewpoint was that I was here as an observer, and I was interested in this and this happening. Okay? That was this. Now what I'm saying is, if I know this I know with probability B, then what information does that give me about A? Okay? And this is this probability. Okay? But why should I pick B? Right? I could pick A just as well. So I can pick this route and then know that A has happened, and then look at how that influences the probability of B. Okay? So the cost of me knowing A is the probability of A, and once I know A, I will have a look at how that influences B. So that's what I call B given A. Okay? So this says B with the influence of me knowing information about A. Okay?
What does this notation mean again? In the beginning, probability A, arrow B?
This is not an arrow, it's just an and. Sorry, I should. Is this a bit more clear, perhaps? Intersection A. So knowing that both of them happened should be equal to me knowing that one of them happened, and then now that I know that it happened, with that influence, I can deduct something about something more about A. Okay. Another popular way of writing this, which I don't necessarily agree with, is, and I think is a bit more confusing, that A given B, I'm just rearranging this formula, is I'm just dividing by the probability of B here. Or am I? Sorry. Yes. So that's going to be the probability of A and B divided by the probability of B. Okay? I think this is a bit clearer because it helps you with this sort of viewpoint, and I think this sort of way of looking at it is a bit more useful. Okay. And there's one really important definition here, is the notion of independence. So we already had mutual exclusivity. That was two things that couldn't happen together, right? Here, independence is different. Independence will be that one doesn't influence the other. Okay? So we define independence by saying that we say that B and A are independent if this is true. Okay? So this is independence. So what this is saying is, I know that A and B are independent of each other because it doesn't matter that I know A. It does not give me any information about B. With me knowing A has happened, B has just as much of a probability of happening as if I didn't know A. Okay? And that's what we call independent. So, to give a couple of examples, So let's say our event space is what Tom Kelsey will drink next morning, and the shirt that Obama will wear tomorrow. Okay? So, me knowing what Tom Kelsey will drink has no influence on what shirt Obama will wear tomorrow, I hope. So I think it's a sufficiently good assumption. So we would say that these two events are independent of each other. Me knowing what Tom Kelsey had drank has no influence on what Obama will wear. In the exact same way, the reverse is true. Me knowing what Obama wore probably does not influence what Tom Kelsey will drink. Okay? Where is this used? Okay, so this is the first thing that I would like to relate to data encoding. Okay, so
just before we, how would that work in the top case then, where you're saying that if you know B, then it does influence A?
Say that again.
So like you just said, if you know what shirt Obama is going to wear, it doesn't influence Tom Kelsey's drink.
Right.
Isn't that only for independence? How does that fit into the, like, how would that example fit into the top one where it does matter?
So that would mean that because I know this, so okay, let's name them. So B is DK's drink, and A is going to be Obama's shirt, or whatever. I don't know. Okay, so now because A has no influence on B, then what I can say is this will get replaced by just A. Okay? So this will mean that these two events occurring, both of these events occurring, is exactly the same as this event occurring and this event occurring multiplied, because they don't influence each other. Okay? If it did have an influence, then it would be slightly smaller. This is generally true. Okay, and it is equal when the two variables are independent of each other. Okay, does it make a bit of sense? Slightly. Okay, let me write it out a bit. So I will write out that equation, inequality, in a bit more. So by definition, this is by definition. So there's no real choice here. We will say that A and B occurring is equal to let's see, to P of A times B given A. Sorry. Okay. But this bit, right? This is some information about B now that I know A, right? So this is more information. I can be more confident in this, okay? So I have this inequality P of B is P, okay? Sorry, did I write this correctly? No, sorry, other way around. So if I know some information about B, that's more than if I just know B, okay? If I'm just looking at B. So then if I substitute this in here, right, then I will get an inequality, okay? So basically this is saying with and without the information. Okay? And what I'm saying is, if the two events have no relation to each other, then because this will be equal, then this will be also equal. Okay? Does that make a bit more sense? This is the trickiest part of basic probability theory, so that's good. Okay, before we run out of time, and we are, I'd quickly like to cover Bayes' theorem, and I think that will be for today. So Bayes' theorem is basically, let me rewrite this back. It's saying that we can relate these things quite nicely. So imagine that I knew a couple of things. So let's see, and it is equal to, I'm just rewriting what's up there. I'll actually rewrite it in the other form, sorry. So I'll just rewrite this one. Probability of B. Okay. So then it is natural to ask, if I know this, can I use this to find out what the probability of B given A is? So basically what I'm saying is, if I know these joint probabilities and I know one root like this, then can I calculate this root? And that's basically what Bayes' formula gives us. Because if we write this form out for B given A, then notice that because of this, I can rewrite this this joint probability as this multiplied form, which is just going to be P of A given B times the probability of B over the probability of A. So basically it's saying is that if I know these other three, I can come up with a fourth thing. Okay? Yeah. That's what the Bayes formula is. I have to apologize, I did not have enough time to prepare an example for this, so if you wish to have a second session, then I would start the second session with an example on Bayes' theorem. But for now, I think I would like to conclude, so I would like to ask you if you have any questions. Or everything is clear, we're all happy. We can now do data encoding. Well, not yet. That's I have a whole section on vectors and stuff that people are confused about. But for those, I wanted to cover these things first because I will use those. No questions? Okay, in that case, thank you very much. I hope you had fun. Cool. Yeah, so please, if you like what you see,